let us conclude and pull these trains together. So, in summary, small variations on the theme of balls and urns are potent in understanding how particles in statistical physics behave. The classical theory, due to Boltzmann and Maxwell, treated particles as if they were distinguishable. What else? It's so completely natural. There's only one thing wrong with it. It doesn't fit the reality at the particulate level. The more refined statistics, due to Bose and Einstein, describe this class of particles called bosons. And these particles are modeled as if they were indistinguishable, but non-interacting. And they occupy urns, but there's no constraint on how many particles can occupy an urn. And these lead to the Bose-Einstein statistics. Another class of particles, the fermions, the particles with half-integer spin, these are modeled by indistinguishable balls with the additional constraint that the particles obey the Pauli exclusion principle. No two particles can be in the same state, can be in the same urn. And a huge mass of nature is explained by this class of particle. All the particles that are known to nature so far fall into either the boson or the fermion category. But of course, this need not be the end of the story. As more and more exotic particles are discovered, as richer and wilder behavior is discovered, we might find evidence, the need for a new theory. Still another model of reality. But that will have to wait upon the event. In this part of the Tableau, we have articulated how we can start with a very basic ball and urn model which arises in commonplace settings and apply it in a rather sophisticated setting, that of statistical physics, and extract beautiful key insights. We now go back to the main thread, our understanding of how commonplace problems lead ultimately to a formulation of the basic tenets of a formal theory of probability. So we shall pick up the thread, the skein again, in part 3 of Tableau 3, coming up next.